This video is a demonstration of using EQR Opt CST Design Studio for port tuning of a 3D FEM model. Here we have a n=10 Combline filter model in CST Microwave Studio. We've added extra ports off the end of each resonator so that we can port tune this model in the circuit theory domain. Circuit theory domain optimization is much faster than trying to optimize this model directly in the EM domain. The initial geometry was generated by the Cavity Combline program, or CCL as we call it, and it is actually quite good for these standard inline Combline filters. It generally sets the resonator screws to be in a little bit too deep, and also it's hard to include the coupling screws analytically, so the design program purposely makes the bandwidth a little bit too narrow so that coupling screws are required. So we've arbitrarily set all the coupling screws here at the start to some depth in between the resonators. So we can solve this in Microwave Studio, and we get a multi-port S parameter file, in this case 12 ports, and we can then export S parameters and import those into Design Studio. And here we have our tuning schematic in Design Studio. So for every resonator we have a shunt capacitor to tune the frequency, and between each resonator we have a series capacitor to modify the coupling. These are inductors in series. The lumped ports that we're using in Microwave Studio, here you can see one of the lump ports, they have a finite inductance, and that inductance can be computed in Microwave Studio using a macro, and we want to then put the negative of that inductance in series with our tuning network here. If we don't include this correction, we'll still converge to a good solution, but it'll take one or two extra iterations to do that. Realize that the goal here is for these tunings to go to zero. So if all the shunt capacitors go to zero or something very close to it, and if all the series capacitors go to zero or something very close to it during the port tuning process, then this path is open circuited, this path is open circuited, and this path between resonators is open circuited, and the value of these corrections doesn't matter. At that point you can make them anything, and because the path to ground or the path in between these two is open circuited, the value doesn't matter at all. So let's take a look at our initial tuning here. If we update this simulation and look at the S parameters, what we've done is with some manual tuning, we've applied some negative capacitance to each one of the resonators in order to basically center the response. And we've set all the coupling corrections just to 1 femtofarad. Notice here that the units on the capacitors are femtofarads. So these corrections at this point are in fact pretty small. This is negative 2/10 of a picofarad. So if we launch the optimizer for Design Studio, we can now bring this response to perfectly equal ripple. So you can see the optimizer is marching through all the variables and computing the sensitivities. For this n=10 Combline, we have 20 variables that we need to optimize. And now it's made its first set of corrections, and already we're seeing the 10 deep return loss nulls in the passband. And the solution here is already quite good. We could probably even stop here, but we'll let the optimization finish. Maybe one more step here. And now it's going to look at the pole positions and make some minor corrections to the pole positions in the passband. So now we're done with the optimization, and we clearly have a passband response that's very nearly perfectly equal ripple. And it's interesting to look at the tunings at this point. Here are the resonator tunings, and if we look at the symmetry from input to output, we notice that the tunings are symmetrical to the nearest femtofarad, sometimes even maybe a little better than that. So this tells us that the S parameter file and the mesh that CST Microwave Studio has generated are both very symmetrical. If the mesh is not symmetrical, the S parameters won't be symmetrical, and our tunings won't be symmetrical. And we can look at the tunings on the couplings as well, and again we see a very high degree of symmetry out to maybe 100th of a femtofarad on the corrections for the couplings. So now the question is, well, how do we translate this to physical dimensions? How do we update the CST model and make it more perfect? Well, I've posted a tutorial on my website. If you go to www.dgsboulder.com and look in the tutorials section, this one right here outlines a procedure to turn those port tunings into physical dimensions. And it's really quite simple. It just involves a simple Excel spreadsheet, and the process converges quite quickly, particularly with the moving mesh feature in CST Microwave Studio. The number of FEM solutions that we need to converge to a almost perfect model is actually quite low. So that's an example of using CST or EQR Opt CST Design Studio for port tuning an FEM model.